So to continue on with the physiology of the respiratory system, we'll talk about pulmonary and alveolar ventilation rates. So we've said that pulmonary ventilation is the process of moving air in and out of the lungs. And if we look at the pulmonary ventilation rate, that's the amount of air that's moved in and out of the lungs, between outside and in your lungs, in 1 minute. So there's a bunch of volumes, but the amount of air that goes in and out in one breath is called the tidal volume. Now it's going to vary with every breath, but it averages with quiet breathing about 500 mils. But if you take a deep breath, your tidal volume just gets bigger. So the tidal volume is the amount of air per breath, and the number of breaths per minute is the respiration rate. So if we look at the tidal volume times the respiration rate, we get the pulmonary ventilation rate. So if about 500 mils times 12 breaths a minute is about 6 liters of air per minute. Now, this is the air that goes in and out. It's the air that you actively have to move. But it's not all the air that reaches the alveoli and the respiratory zone. Some of the air is still in the conducting zone. When you breathe in, you have to fill the trachea, and then that air doesn't go any further than the trachea. And then when you breathe out, that's the first air to leave. It's the last to arrive, and it's the first to leave. And it never makes it all the way down to the respiratory zone. So we call this the dead space. It's the space of the lumen of the conducting zone, where there's no exchanges happen. Now, in most people, this is about 150 mils. So really, that pulmonary ventilation rate includes the air that you're moving in and out of the lungs, but it includes the dead space. So really what we care about is alveolar ventilation and the alveolar ventilation rate, which is the amount that's actually reaching the respiratory zone in a minute. So really what that is the tidal volume minus the anatomical dead space. So then that's really the amount that makes it to the respiratory zone, times the respiration rate, and that gives you the alveolar ventilation rate. So if our tidal volume is about 500, 150 is the dead space, so then it's 350, makes it to the alveoli. 12 breaths a minute is 4.2 liters a minute, so about 4 out of 6 liters. So really in a minute we're moving almost 2 liters of air that doesn't actually make it into the space. I'm going to pull up a chart from a different PowerPoint and to illustrate how deep breathing maximizes alveolar ventilation. So this is a chart from a different textbook. So if we say dead space is 150, tidal volume is 500, and so that's normal rate and depth. And let's say that you're breathing 20 breaths a minute instead of 12. That means your minute ventilation rate, your pulmonary ventilation rate, is 10 liters of air per minute. But 500 minus 150 is 350 times 20 is 7 liters of air per minute, or about 70% of the air gets to the alveoli. If you go to slow, deep breathing, and so you double your tidal volume to 1,000 mils, that means 850 mils are in the dead space, but you've as makes it to the alveoli, because only 150 is in the dead space, and you slow your breathing down to 10 breaths a minute, you're still moving 10 liters of air per minute, but 8,500, so 8.5 liters, is actually making it to the respiratory zone. If you go to rapid shallow breathing, like you're upset or something, and you change your respiratory rate to 40 breaths a minute with a tidal volume of 250, your dead space is still 150, so you're only moving 100 mils per breath. 100 times 40 breaths is 4,000, as opposed to the 10,000, the full 250 times 40. So you're only getting 40%. So that's why, if you go to yoga class or anything, it's like breathe slowly and deeply, because it's that much more efficient. It's really crazy more efficient. Let's go back to this. So deep breathing maximizes the alveolar ventilation rate. Now, the dead space is going to change in pathology. If you have emphysema, for instance, and so you lose some alveoli, you will have fewer alveoli actually participating in gas exchange, so this dead space will go up. The physiological dead space will go up. So if you can picture somebody with emphysema, and so say their dead space goes to 250, well, rapid shallow breathing of 250 of tidal volume means that they're getting 0 to the alveoli. They have to breathe much more deeply. And so this is a real consideration with a lot of diseases, either temporary or chronic. So because of that, we use spirometry to measure these things. And we look at different volumes. So we've already discussed that the tidal volume is the amount of air brought in and out per breath. Just like the tide goes in and out, breath goes in and out, that's the tidal volume. But as you know, take just a normal breath and hold it, and now take a deeper breath. There is a volume in your lungs that can take more air that you don't normally use. And anything you don't normally use is held in reserve. So we call this the inspiratory reserve. It's the amount of air that you can inhale beyond the tidal volume. And that just is a measure of how compliant the lungs are and how much they can fill. So the inspiratory reserve is air that you can breathe in, but you don't normally. If you just let out your normal tidal volume to a quiet breath out, and then blow some more, like you're going to blow out birthday candles, there's still more air in your lungs. And we call that the expiratory reserve. It's air that you can breathe out, but you normally don't. But you can. And that really is looking at how elastic the lungs are, like how good the lungs can contract. Now there's an amount of air that you can't breathe out. It just stays in the lungs as long as the lungs aren't collapsed. And that's called the residual volume. It's the amount that you can't breathe out even if you want to. So we have the amount that we do breathe. We have the amount that we can breathe in, but we don't. We have the amount that we can breathe out, but we normally don't. And then there's the amount that we can't breathe out. It just stays there no matter what, the residual volume. Now, these are the 4 volumes, but there are these capacities. And capacities are combinations of these volumes. So if we look at the inspiratory capacity, that is how much can we breathe in. So that's the amount that we do breathe in plus the amount that we can, but we don't. So that's the tidal volume and the inspiratory reserve. Those two things together are called the inspiratory capacity. It's the amount that's possible after a normal tidal out. The functional residual capacity is the amount that's left in the lungs at a normal breathe out. So that is the amount that we can breathe out but we don't, the expiratory reserve, and the amount that we can't breathe out, so the residual volume. So the expiratory reserve volume and the residual volume together are the functional residual. Now the vital capacity, vital means life, so as long as you're alive, you can exhale to the bottom of the reserve volume, so right down to the residual volume, and then breathe in right through, refill the expiratory reserve, do the tidal volume, and fill the inspiratory reserve volume. Those three things together are the total amount of air that a person can exchange through forced exhaling and forced inhaling at the one right after the other. So it's the vital capacity. And then the total lung capacity is the sum of all four volumes. It's the total capacity of the lungs. We also look at the rates that these things, so in spirometry we look at the rates. So the forced expiratory volume is the amount of the vital capacity that you can get rid of in a period of time. So usually it's 1 second. So the forced expiratory volume is how much air can you actually blow out in 1 second. And that really is a measure of your ability to do it. People with COPD have trouble because of the obstructions to get it out. The maximum voluntary ventilation is the greatest amount of air taken in and expelled in 1 minute. So breathing as quickly and deeply as possible. So these are measures of respiratory disorders. So if we look at the normal here, and it's interesting because spirometry you always read from the right to the left. So you start here and you go this way. This is breathe in, breathe out, all the way out, all as much as you can. Blow up the balloon, empty your lungs. Then breathe in and breathe out. Breathe in, breathe out, breathe in, breathe out, breathe in. All the way in and fill your lungs, and then breathe out. Breathe in, breathe out, breathe in, breathe out, breathe in, breathe out. So, inspiratory reserve volume, tidal volume, expiratory reserve, residual volume. Vital capacity is everything but the residual. Total lung capacity is all four. The inspiratory capacity is tidal volume and inspiratory reserve. The functional residual is expiratory reserve volume and residual volume. There. Okay. If we look at the partial pressure of oxygen in the alveoli, according to some laws, the total atmospheric pressure is divided proportionally amongst the proportions of the gases in the air. So if we say that the air around you is about 21% oxygen. The and the total pressure is about 760. Then it's about 100, and it's actually about 159 is the partial pressure of oxygen. But you're only going to bring so much atmospheric air into your lungs because the functional residual has got more carbon dioxide and less oxygen. So what ends up happening is the partial pressure of oxygen in the alveoli is around 104 millimeters of mercury. The partial pressure of oxygen in your blood coming from the veins, so on the right side of the heart, is about 40. So this is a pressure gradient, 104 to 40. And so oxygen will leave the air in the alveoli and enter the blood to try and equalize that out. It moves down its partial pressure. And it will do that until an equilibrium is reached. And then you breathe out and you breathe in and you get the PO2 back to 104. Now, the CO2 in the alveoli, in the air it's very low, but in the alveoli, because of the residual, the functional residual, it's fairly high. It's about 40 millimeters of mercury is the partial pressure of carbon dioxide. In the blood from the right side of the heart going into the pulmonary arteries, it's about 45. So it's higher than in the lungs. So carbon dioxide will diffuse from the blood into the air of the alveoli. It moves down its partial pressure gradient and it will reach an equilibrium. Excuse me. So, and the body is very good at bringing blood and air to the same place at the same time. So ventilation changes by bronchodilation and constriction to bring air to particular areas of the alveoli, and perfusion is arterial dilation and constriction. So these two things match, and it all revolves around how much CO2 is there. Okay, so I'm not going to be worried, as you know, about any of these pathologies. That's for pathology class. So the idea here is we bring blood and air to the same place at the same time. The problem is that if you can't bring air to it because of a lung disorder like emphysema, then you don't bring blood to there, and that increases the pulmonary blood pressure because there's less places for the blood to go. It increases the resistance. And so oftentimes people with breathing difficulties also end up with vascular difficulties because of it. Now, internal respiration is the exact same thing as external respiration, except it happens at the tissues. So the partial pressure of oxygen in cells of the tissues is about 40, and that's because you use up all kinds of oxygen making ATP. In the capillaries, at the arterial end, it's about 95 because it's equaled out to someplace around 100 and you lose a little bit. So so oxygen will move down its concentration gradient, leave the blood, and go into the cells. And so it will equalize fairly quickly. And so blood, partial pressure of oxygen, will become 40 because it equalizes. It stays fairly constant. CO2 does the other, because CO2 is made in the cells in aerobic respiration, and it's about 45. In the capillaries, it's about 40, so CO2 will leave the tissues and go into the blood. And then the blood transports it. So blood is not very soluble, or oxygen is not very soluble in blood, so very little goes into solution in the plasma. So that's why we need hemoglobin in the red blood cells. About 98% of the oxygen goes bound to the hemoglobin, to the iron molecules in hemoglobin. And about 2% actually goes in the plasma. Carbon dioxide, on the other hand, will go into the plasma. 7% of that will stay as CO2. About 23% actually will go onto the hemoglobin and join onto the globin part, like onto the protein part, not onto the heme part. But most of it, 70%, the carbon dioxide has a chemical reaction with the water, so CO2 plus H2O becomes H2CO3, which is called carbonic acid. And then the carbonic acid dissociates and becomes bicarbonate ions and hydrogen ions. And the hydrogen ions lower the pH. So when we get to the lungs, the oxygen or the carbon dioxide leaves, the dissolved carbon dioxide leaves, the carbon dioxide attached to the hemoglobin leaves and goes into the air, and a bunch of it, of the bicarbonate, then recombines to become carbonic acid, which then breaks apart and becomes CO2 again. So that equilibrium, and that's how we breathe out. So we transport oxygen mostly on the hemoglobin, carbon dioxide 7% dissolved, 23% attached to the hemoglobin, and 70% as bicarbonate. So the hemoglobin, as I said, oxygen is attached to iron, carbon dioxide to the globin. Now, what's interesting is that having one of these things on the hemoglobin changes the ability to carry the other one. Let's say the other two, because hydrogen ions as well. But we're mostly concerned about the two. So really, each hemoglobin will take 4 oxygens, because there's 4 irons, and as saturation increases, it causes it makes it easier for the next oxygen to bind, and we call this the saturation curve. So really what it is that we end up with this S-shaped curve. So it's easier for oxygen to bind to hemoglobin in a high oxygen state. And it's more difficult for it to bind in a low oxygen state. So what it means is that the hemoglobin is almost designed to be able to load oxygen on in a high oxygen state and unload it in a low oxygen state, so that if the blood gets to tissues that haven't used up very much oxygen, it's stingy about giving it more. So you can just read through this, but hemoglobin saturation is usually at about 98% as it passes through the lungs. We don't ever make it to 100% unless we are in a hyperbaric chamber. But what you want is about 98%, which comes out to just around 100 millimeters of mercury. I don't really care about altitude sickness and things. As the oxygen passes, it gives up about 25% of its of the oxygen as the blood passes through the capillaries. So this means that there's a reserve of oxygen being carried. And that's why you get about 3 minutes of not breathing and still being able to supply oxygen, because each pass gives up about 20%. This is interesting. As temperature increases, it's more difficult for the hemoglobin to hold on to oxygen. So, but when you think about it, tissues that you are using, so say you're on the Stairmaster, the gluteus maximus muscle is used up a lot of oxygen and is warm. So the blood will enter that. It's a low oxygen state, so that means that the hemoglobin will give up oxygen more readily. It's warm, so the hemoglobin will give up oxygen even more readily. There might be some lactic acid, so any acidity will bind to the hemoglobin and cause it to be able to give up oxygen more readily. It's called the Bohr effect. So your glutes on the Stairmaster will be acidic, warm, and low oxygen. So you will give up oxygen quite quickly. So we call this shifts in the saturation curve, moving it left, moving it right. It shifts right with increased temperature and increased hydrogen ion, so decreased pH. It shifts left, cooler and alkaline. Now, carbon dioxide is not as affected by that as much, but carbon dioxide affects the affinity for oxygen as well. So if there's more carbon dioxide, it shifts to the right as well and gives up. So your gluteus maximus will have lots of carbon dioxide, which will shift to the right and make it easier for the blood to give your glutes oxygen. If you're just being a couch potato, you're playing PlayStation and you're not using your glutes, the blood will get there. Your glutes will be cold, not acidic, it'll be slightly alkaline. There will be plenty of oxygen and not very much CO2, so it shifts everything left and means that the blood will be stingy about giving that oxygen up, and it will save that oxygen to give to other tissues.